Okay, so hey there everyone. Today we are going to solve this question, which is plot the instantaneous junction temperature. And the question given to us is to plot the instantaneous junction temperature given the device power loss graph, right? So the power loss of a device is shown in this figure, as you can see in this figure, and we have to plot the instantaneous junction temperature rise above the case. Okay, and we are also given that the power at pulse P2 at pulse 2 4 and 6 is equal to 0, and power at pulse 1 3 and 5 is equal to 800, 1200 and 600 watt respectively, as we can see in this figure. And now for and we are also given that the T1, T3 and T5 is equal to 1 millisecond. It means that the pulse 1, pulse 3 and pulse 5, the duration of this pulse, all the three pulses are equal, which is equal to 1 millisecond. And we are also given impedance is also given to us for the first pulse, third and fifth pulse as 0.035 degrees Celsius per watt, also given with the impedance of the pulse 2, 4 and 6 as 0.025 degrees Celsius per watt. Okay, so the impedance for all the pulses, odd as well as even pulses, are given to us. And now with the given values and with the given power, we have to plot instantaneous junction temperature rise above the case. The first of all, how we will proceed. Okay, so in this, first of all, to plot the junction temperature rise graph, first of all, we have to find the junction temperature at each of the points, right? Suppose here this is 1 millisecond, then 1.5, then 2.5, then 3 millisecond, then 4 millisecond, after that 4.5 milliseconds. So for all this point, for all this time period, we have to first find the junction temperature. Once we are done with the finding of the junction temperature at each of this time period, that is 1 millisecond, then 1.5, then 2 and so on, after that we can easily plot the graph of it. One must be clear with one of the equation, that is the junction temperature at the end of mth pulse. Okay, so junction temperature, junction temperature at the end of mth pulse, it is given by one formula, and that formula must be clear to you. That is the prerequisite for solving this question. If this formula is clear to you, this question is nothing but a cakewalk. So the junction temperature at any particular time t is equal to Tj0, that is the initial junction temperature, plus Z1 into P1 plus Z2, P2 minus P1 plus Z3, P3 minus P2 and so on. And if I have to make this formula a little bit simpler, I can write it as Tj or at time t is equal to Tj0 plus sigma n is equal to 1, 2 and so on up till m, and is equal to Zn Pn Pn minus 1, right? So this will be our formula, and this formula will give us the junction temperature at the end of the mth pulses, right? So this formula must be clear before proceeding this question. Now we will start with the solving of this question. So first of all, as I said, we will find the junction temperature for each and every time, like 1 millisecond, then 1.5, then 2 millisecond and so on, right? So let's start with first finding the junction temperature at the end of the first pulse. So where is our first pulse? So this is our first pulse of 1 millisecond. So first of all, we will find the junction temperature at the end of this first pulse, right? So j t is equal to 1 millisecond, right? It means that we are going to find the junction temperature difference at the end of the first pulse, which is given to us, and this pulse is ending at 1 millisecond. Now according to our formula, delta Tj, it is equal to Tj at any time t, and the time which we have taken over here is for the first pulse, that is 1 millisecond, minus of initial junction temperature Tj0, right? So this is equivalent to delta Tj, that is the difference in the junction temperature. Okay, so now delta Tj at t is equal to 1 millisecond, what it will be equal to? It will be equal to Z1 into P1, as we have discussed the formula earlier. If you just keep the m is equal to 1 in it, you will get the formula as Tj is equal to Tj0 plus Z1 P1. You will get this formula if you put m is equal to 1 in the formula that we discussed earlier. And now we have to find the delta Tj. So you have to write Tj minus Tj0 plus is equal to Z1 P1. Now Tj minus Tj0 is equal to delta Tj is equal to Z1 P1. So this is how we are getting over here this Z1 P1. I hope we are clear with this. The value of Z1 given to us, Z1 is given to us as 0.035 degrees Celsius per watt multiplied by power P1. Power P1 means the power for the first pulse, which is given to us as 800 watt. So multiplied by 800 watt, and what we will get? We will get as 28 degree Celsius. If you solve this multiplication, you will get the answer as 28 degrees Celsius. It means that a junction temperature at the end of the first pulse, it means the junction temperature at t is equal to 1 millisecond will be equal to 28 degree Celsius. Now similarly, we are going to find the junction temperature at the end of the second pulse, third pulse, fourth, fifth pulse, right? So now let's start finding for the other pulses also. Now let's find the delta Tj for the t is equal to 1.5 millisecond, right? Now t is equal to 1.5 millisecond. If you carefully observe over here, the 1 millisecond is for the first pulse, right? And for the 0.5 millisecond, there is nothing, there is zero. So this is the second pulse. If you see, if you observe in the question, it is given to us as that p2 p4 p6 is equal to 0. This is the p2. At this point, at this pulse, the power is equal to 0, right? So that is one thing that you must keep in mind. So delta Tj, t is equal to 1.5 millisecond. If I put the, means basically what I want is the junction temperature at the end of the second pulse. If I want to find T, if we want to find the junction temperature at T is equal to 1.5 millisecond, which is equivalent to finding junction temperature at the end of the second pulse, because our second pulse is ending over here and the time over here is 1.5 millisecond. 1 second for this, 0.5 this. So total 1.5 millisecond is the time over here, and our second pulse is also ending over here, right? So if I want to find the junction temperature at 1.5 millisecond, I will simply find out the junction temperature at the end of my second pulse. Okay, so now according to our formula, uh, let me write the formula over here so we don't have to look after it again and again. So what we will do, we'll simply put m is equal to 2 because we want to find the delta Tj, that is the difference in junction temperature at the end of the second pulse. So if we put m is equal to 2, what we will get? We will get it as Z1 P1 minus P0 plus Z2 P2 minus P1. Now P0 will be equal to 0. So it will again simplify like Z1 P1 plus Z2 P2 minus Z2 P1. Now in the question we have been given that the P2 is equal to 0. You can see over here P2 is equal to 0. So again now this term will become 0. So now the formula will become Z1 P1 minus of Z2 P1. Now Z1 P1 is nothing but 28 degrees Celsius that we have calculated earlier. So I will write 28 degrees Celsius minus Z2 into P1. Now 28 degrees Celsius minus Z2, what is the value of Z2? So it is 0.025 multiplied by the power P1. What is power P1? It is equal to 800 watt. So 800 watt. So after solving this, we will get the answer as 8 degree Celsius. So, so this is the junction temperature at the end of the second pulse, or I can also say that it is a junction temperature at the end of t is equal to 1.5 millisecond. Now similarly, like what we have done over here, now similarly we will find the delta Tj for t is equal to 2 millisecond, 2.5 millisecond, sorry, 2.5 millisecond. Okay, so 2.5 millisecond, it means now 1.5 over here, and now 2.5 means it will over here somewhere, 2.5 millisecond, right? So if you look at over here, this is the third pulse, this is the first, this 0 pulse second, this is the third, this is the fourth, this is the fifth. So if you look over here, this is the third pulse. If we want to find the junction temperature at 2.5 millisecond, it will be equivalent to finding the junction temperature at the end of the third pulse. Can I say this? Yes. So it will again will become like this, that if you put m is equal to 3 means at the end of the third pulse, so you will get something like this, like z1 p1 plus z2 p2 minus p1 plus z3 p3 minus p2 and so on, right? Now if you again simplify it a little bit more, if you just open the brackets, you will get like this, z3 p3 minus z3 p2 and so on, right? Now z2 p2 is our 0 since p2 is equal to 0. Now over here also z3 p2 term will be equal to 0 since p2 is 0. So our finally our formula will become z1 p1 plus z3 p3 minus z2 p1. Now we have already solved this, z1 p1 minus z2 p1 is equal to 8 degrees Celsius. So I can directly write it as 8 degrees Celsius plus of z3 p3. So if you just put the value of z3 and p3, it is equal to 0.035 multiplied by 1200 value of p3, and if you solve this, you will get it as 50 degree Celsius, right? That is the delta Tj at t is equal to 2.5 millisecond. I hope it is clear till this point. Now similarly, what we have done for 1 millisecond, 1.5, 2.5, similar thing we will do for the rest of the points, that is for delta Tj with t is equal to 3 millisecond. We will do the same thing as we have done over here. For 3 millisecond, it will be equivalent to the junction temperature at the end of the fourth pulse, right? So we will do the same thing. I am not doing it over here again, you can do it, and the answer that you will get will be equal to 20 degrees Celsius. Now similar thing for delta Tj, for t is equal to 4 millisecond, if you do, you will get the answer as 41 degrees Celsius. And for delta Tj, t is equal to 4.5 millisecond, if you do, you will get the answer as 26 degree Celsius. Okay, once you have got all this value for t is equal to 1 millisecond, 1.5, 2.5, 3, 4 and 4.5, now is the time to start plotting the plot for the junction temperature versus the time in millisecond. So now let's plot the graph. I have noted down all the junction temperature at different time periods that we have obtained at one place. So now let's start the plotting of our junction temperature plot. The plot of our junction temperature rise after each and every time that for which we have calculated. Okay, so let me quickly mark each and every time on my x-axis first. So t is equal to 1 millisecond. We have junction temperature as 28 degrees Celsius, which will be somewhere over here near to 30 degree. At 1.5 we have 8 degrees Celsius, it means below 10. At 2.5 millisecond we have 50 degrees Celsius, that is at somewhere over here at the top. At t is equal to 3 millisecond we have the junction temperature as 20 degrees Celsius, so it will be exactly at 20. At t is equal to 4 millisecond, we have 41 degrees Celsius, just above 40. And at 4.5, we have 26 degrees Celsius. So it will be somewhere in between 20 and 30. So like this. Now we have to just connect these dots. Okay. Okay, so after joining all these dots, we will get our plot something like this. So this is our final plot. That is the plot of junction temperature rise versus the time that we wanted as our solution. So that's it. You're helpful. Then please drop a like. And if you have any type of query, please feel free to drop in the comment section. And I will see you in the next one.